The last topic for today is solving least squares problems. So the problem I'm going to look at is I have a data set. So in this case, I took some sort of market return, so S&P 500 returns, and I've plotted them on the x-axis. And then I've taken the returns for one specific asset, so it's going to be shares of Citigroup, and I've plotted those on the y-axis, and so those are the black dots here. And what you want to do is, what the goal of this is I want to find the best fit line here, and the slope of that best fit line is going to be called the beta for this particular asset. So it's a way of relating the returns on one particular asset to the returns in the market. And so what I've drawn here with the red line, hopefully you look at that and realize that the red line is probably not the best fit because most of the data is up above it. So this is just my guess at a best fit line. So I just wrote a line that's supposed to be a y tilde is equal to alpha plus beta times x. And what I want to do is I want to find an alpha, and I'm going to call it an alpha hat, and a beta hat that give me the line that's somehow closest to all of these black dots. So in general, how I'm going to approach this is I'm going to think that I have a set of m points, so xi, yi. So each dot here, just the x coordinate, suppose this dot up here was the fifth point, then x5 would be the x coordinate of this dot. Y5 would be the y coordinate of that dot. So I have this set of m points, so there's m dots here. Since these are monthly returns from 2010, there will be 12 dots. So m will be equal to 12. And I want to find this best fit line. Y hat is equal to alpha hat plus beta hat x. And my criterion is what I'm going to define this yi hat to be the value on the line at the same value x as each one of these data points. So what I end up, if I look at the one on the right here, I'm taking not the perpendicular distance to the line, but the vertical distance to the line. So that's just going to be yi minus y hat. So the actual point, this black dot, minus the point on the line at the same x coordinate. So that would be this red dot here. And I'm going to take that difference, and because that could be positive or negative, I'm going to square that to get something only positive. And then what I want to do is I want to choose the line that's going to make that square is small. So I'm going to sum up all of those deviations. That's going to give me some positive number. And I want to choose the line that's going to make that number as small as possible. So I want to minimize this sum of squares. And so the points on the red line here, I can write those as alpha plus beta times xi. So for any x, the point on the line is just given by this. And so I'm going to replace this y hat with a formula that gives me y hat. And I'm going to look for values, alpha hat and beta hat, so that when I plug in alpha hat for alpha and beta hat for beta, this sum is the smallest I can possibly make it. So that's kind of the graph picture. And now I want to see if I can set this up as a matrix problem. So I'm going to call that, I'll call this the row picture because each one of these points is sort of described by xi, yi. And so if I think of xi, yi as rows, I can draw the points like that. For solving it, it turns out to be useful to write this in the column picture. So I'm going to take my y values, y1 up to ym, and I'm going to call that a vector y. Do the same thing to get a vector x. So x is just the vector of all the x values. And then I'll let E be a column vector of m1s again. And so what I end up with is I can write y tilde. So these are the points on the line now. I can write that as a linear combination of my vector of 1s and my vector of x's. So I have y1 is equal to, so alpha times 1, so y1 is equal to alpha plus beta times x1, and that holds for each row. So instead of thinking of it as rows, I can now think of it as this linear combination of this column of 1s and the vector x. And then I can put those two vectors together into a matrix and express this vector y tilde as this matrix with one column of 1s and then one column being my vector x times the vector alpha beta. And then I'm going to do a terrible abuse of notation and refer to this vector alpha beta also as just beta. So when beta is a vector quantity, it means this vector alpha beta. And when it's a scalar quantity, it means this second element of alpha beta. And now remember, I want to minimize. So this is the distance between the vertical distance between the actual point and the point on the line. So the y tilde over here is the point on the line, and the yi is the actual point. I'm going to take that distance and square it and sum it up, and that's going to give me the criterion, the thing that I want to minimize. But that's actually just the distance between these two. That's the definition of the distance between two vectors. So if it had a square root here, it would actually be the distance between y and y tilde. So without the square root, it's the squared length of the vector that I get when I subtract y tilde from y. And then remember, I can write y tilde, so what I've just done up here, as x beta. Oops. So this is the problem I want to look at now. So the y is given. I know what the y values of my points are. The x is given. I know what the first column is, because that's always 1s. I know what the second column is. That's the x values from my points. And I want to choose beta. So I want to choose values of alpha and beta to make the length of this vector as short as possible. So I'm going to use something called a QR factorization to help me do this. And so if A is an m by n matrix with linearly independent columns, a full QR factorization of A is just going to be a product of an m by m orthogonal matrix Q and an m by n upper triangular matrix R. And so remember, when I have more rows than I have columns, it's still just the 1, 1, 2, 2, 3, 3 elements that are non-zero, and everything where I is not equal to j in this matrix R has to be 0. And my factorization will then be A equals QR. So Q is orthogonal, R is upper triangular. And it turns out that, that this most of the time works. And in fact, if you allow some of the diagonal elements of R to be 0, it always works. And now I want to minimize, so this is from the last slide, I want to minimize y minus x beta. So I want to choose the elements of beta to make this length, this vector, as short as possible. And so the standard rule that I have is when I can factor a matrix, I'm going to put my factorization of the matrix in where I used to have the matrix. So I'll replace x. So here QR is QR factorization of this matrix x. So I'll replace x with QR. And it's a little tricky to see how that's going to help us right now. But we have to remember one other thing. So first of all, Q is m by m, R is m by n, and then beta is n by 1. So in this case, Q is 12 by 12. So for my example that I'm working on, I have 12 data points. So Q is 12 by 12, R is 12 by 2, and beta was alpha beta, so 2 by 1. So the whole product is going to be 12 by 1, because the first The first dimension is a 12, and the last dimension is a 1. So this is just a vector. Y is a vector. So when I do this subtraction, this is still just a vector. And what happens when I multiply a vector by an orthogonal matrix? Or what happens to the length of that vector? Well, one of the really nice properties of an orthogonal matrix is that length stays the same. So the matrix I'm going to choose to multiply this by is going to be Q transpose. So if I have Y is equal to QR beta, so this thing I just argued was a vector. Q transpose is just going to be some sort of high-dimensional rotation of that vector that leaves the length of the vector unchanged. But now I can use the left distributive property here, so I can write this as Q transpose Y minus Q transpose QR beta, which is just going to be Q transpose Y, so this is another vector with 12 elements in it, minus R beta. And R, remember, is now this matrix, so in my case it was 12 by 2, and only the upper triangular bit can be non-zero. So it has 3 non-zero elements in it, and it has 21 zeros in it. So this is actually a pretty easy thing to deal with. So now what I'm going to do, just so I don't have to keep writing Q transpose Y all the time, I'm going to let U equal Q transpose Y. So this is just the rotation of my Y vector. So it's still just a vector with 12 elements in it. And the picture is going to look like this. So I have U minus R beta is going to be U1, U2, U3 minus R. And then my vector beta I can write out again. So scalar alpha in the first position, scalar beta in the second position. And then I can go ahead and just do the math here. So I have the first element. So I can do this multiplication here and then do the subtraction. So here I'm going to get R11 times alpha plus R12 times beta. And then I'm going to subtract that from U1. So in the answer I have U1 minus R11 alpha plus R12 beta. In the second position, I'm going to have U2 minus 0 times alpha minus R22 beta. So in the answer over here, I get U2 minus R22 beta. And then for every other element here, I'm going to have 0 times alpha plus 0 times beta. So the rest of U stays unchanged. So alpha and beta affect only the first n elements. So in this particular case, n is 2. So they only affect the first 2 elements of this vector U minus R beta. And remember, I'm trying to minimize this thing, U minus R beta. And so what do I mean when I write the length of a vector? Well, I mean the first thing squared plus the second thing squared. So this is, the squared length of a vector is just the length without the square root symbol. So that's going to be U1 squared plus U2 squared plus U3 squared. So the length of this vector over here is going to be this thing squared, so that's what I've written here, plus this squared, that's what I've written here, plus U3 squared plus U4 squared, so plus everything else squared. But the only thing here, if I look at this closely, I can now, by choosing alpha and beta, I will never affect what happens over here because these have no dependence on alpha and beta. So I have one term that depends on both alpha and beta, and one term that depends only on beta. And they're squared, so they have to be positive or 0. So the smallest I can make this thing is if this thing is 0 and this thing is 0. So I'm going to do essentially just back substitution. First, I'll choose beta so that U minus R22 beta is equal to 0. That gives me a fixed value of beta, and it makes this term 0. Then I'll plug that value of beta in here and choose alpha so that this quantity is 0. And so then by choosing that particular value of beta and that particular value of alpha, I'll have made both of these terms 0, and that's going to be the shortest that I'm able to make this vector. And this vector has the same length as the vector that I was trying to minimize in the first place, so that vector alpha hat beta hat is going to solve this problem. And so it turns out I can find alpha hat and beta hat just by solving the linear system. So I just have to take the first two rows, or the first n rows in general of this matrix R, and then the solution to this linear system, alpha hat beta hat, are going to be the slope and the y-intercept that I'm after. And since R was designed to be upper triangular, this system is already upper triangular, so I can solve this directly just using back substitution. And so then I have an R example of doing this. So to get the data that I had in the beginning, I use the QuantMod package, got the data for Citigroup. This is the symbol for S&P 500. These next two, just turn those into monthly returns for the year 2010. The X variable is going to be the returns on the market, so the returns on the S&P 500. And then I need to add a 1 in front of that to make my matrix X. So this function cbind just sticks a column of 1s in front of that vector. So X is now my 12 by 2 matrix with a column of 1s and then my vector of X's. Like the singular value decomposition and the eigen decomposition, QR function gives me back a list. So I'm going to save that in QRX. And then I'll use this function QR.Q to get the Q matrix. This function QR.R to get the R matrix. And then if you wanted to, you could check that you did it right by saying all equal Q percent star percent R comma X. That would just check that those two matrices have the same value. So then I'll make a vector U that has Q transpose times Y. So the returns on my asset are the Y variable. And then I'll solve for alpha hat and beta hat just by solving that square system of the top square of R. So the 2 by 2 block at the top of R and the first two elements of U. And that gives me 0.017 as the alpha hat estimate and 1.33 as the beta estimate. And then I'm just going to compare that with the built-in least squares fitting function. So there's a function called lsfit, and I can give it the x variable and the y variable. And note that it also gives me 0.017 for the alpha and 1.33 for the beta. And this is the fit we end up with. So the red line was my initial guess. It's actually just goes through the origin and has slope 1. So it's sort of saying that the market and the asset behave similarly. And the blue line is the least squares fit for the Citigroup returns on the market returns.